So since current by definition is moving charge, then of course you're going to have, so if you have a charge that's moving, so if you look at the equation, force equals Q B crossed into B, what I can do is divide this by T, multiply this by T, divide this by T, multiply this by T, and then I can say Q over T is the current. And then V times T, the velocity that the charge is moving times the time, is the length of the wire. Okay, so now I have a new equation that works for current carrying wires. So now if there's a magnetic field that is, let's say, into the board, what's the direction of the force on that wire? So then I do the length vector. So the length vector is going to be basically in the same direction as the current. So the length vector is like this. The current is moving that way. L crossed into B up. So the force on the wire is going to be this way, right? And then if the magnetic field was out of the board, then you just do, oh, how should we do it? Yeah. Current I crossed into B down. I see. Yeah, there's no other way. This one causes some pain. I crossed into B. The thumb is down. F. Right? So you could have one quick application of this is that you can have a wire, let's say, that is carrying current from west to east, let's say, 1.2 amps. So in this picture, this is west, this is east, and then into the board means towards the ground. So towards the ground. So I could say, what should the direction and magnitude of the B field be so that the wire levitates? So let's say we don't want this wire sagging due to its weight. So we don't want it to be kind of like this wire, you know, if you have a wire like this, see how it sags like that. So we want it to be straight like this. So then we want so since the gravitational force is into the board, right? So this is mg, gravity is into the board. We want the magnetic field, the force of the magnetic field to be out of the board. So which direction should I make the magnetic field? In order for the force of the magnetic force to be out of the board. Let's see, if the magnetic field is this way, what would the direction of the magnetic force be? Right, I crossed into B, out of the board. There you have it. Yeah. So it's kind of like trial and error. I'm going like this, current I, because in this case, the current is already given. So you can say, okay, the current I crossed into B, right? And then this is the direction of the force. And that one can overcome the gravitational force. You see, so then we want B to be towards the north, which actually it is, right? Let's see here. So we want B should be towards north direction. Okay, so now what should its magnitude be? So then I could say F equals ILB sine of theta. So this is going to be the L vector, and this is going to be the angle. So it's just 90 degrees. So then ILB sine of 90, and that should equal mg. Mg is into the board. Yeah, let's see. So the force of the magnetic field is going to be out of the board. And then mg is into the board. So ILB sine 90, that's equal to mg. And this is equal to 1. Okay, so I guess some things have to be given to us. Let's see, the mass of the wire, let's say, is 100 grams. Let's say the length of the wire is 60 centimeters. That the current was already given, 1.2 amps. I think that's it. So now we could find the B. 1.2, length is 0.6 meters. B is going to be, well, we're solving for B. mg, so 0.1 times 9.8. And then that tells you how strong it should be. Yeah, that's pretty strong. 1.36 Teslas. So you can have the wire levitating. It's in the chapter 29 playlist.
All right, we are here.
This is years ago.
I want to demonstrate one of the very interesting effect of magnetic force. I actually do this problem in my class. So I have a wire here, a power source, connected with a rheostat. The rheostat is going to change the current. Then the wire is coming over here. It's going through this wire. And then this one here shows us the current. Right now we have a current of about 1.6 amps. Okay, so now as I increase the voltage, the power source, the current through the wire is going to increase. The current is flowing this way from here to here. Then there's a magnet here whose north pole is on this side. The south pole of the magnet is over here. It's a pretty strong magnet. So the magnetic field lines are coming this way. So this is a great way of also testing the right-hand rule. So the current is coming this way, the magnet is coming this way. So if we do the right-hand rule, I do the cross product of I crossed into B, and it goes up. Okay, so I'll do that again. The I is this way, the B is this way, so I cross it into the B, and the force is up. So if I turn the power supply up, you should see this wire starting to move up, starting to levitate. So we're going to counteract the gravitational force on the wire, and we're going to have the wire levitate. So this also shows the principle of magnetic levitation. So let's see here. I'm going to up the current. You could already see something happening,
Wow. Isn't that cool, guys?
starting to go up. Very interesting here. And I can have it so that it's actually floating in between the two poles of the magnet, sort of hovering in the middle, right there. Very interesting. And then you go up, 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 more current, more current, more current. It starts to float. So this is the age of the future here. Magnetically levitated cars, trains. And we could have go more up, more up, more up, more up. I don't want to burn anything, so we should probably not go too high. But you see, you're counteracting its gravitational field. So we were able to test the right-hand rule and the force on the wire. Okay, thank you.